Okay, let's do this. Yeah, here we go. 2.3. It's kind of funny. We're starting chapter 5, but there's this whole section I want to talk about in 2.3. It was composition of functions, and you can go do this homework. I got this homework set up as part of chapter 5's homework. Yeah, you never did this before, maybe. I mean, maybe you have in some algebra class, but watch this. If I have a function, 4x minus 7, and then I have another function, g, 2x squared plus x, 2x squared minus x plus 3. This new thing is I want to compose these functions. And that is this. Check this out. It's f. Okay, what we did talk about back in chapter 2, we said we could add two functions. You can add functions. You can subtract functions. And that's all. We kind of did that. It was kind of easy. You can multiply functions. But what? And you know what the symbol for add is. You know what the symbol for multiply is. Okay, anyway, check this out. This little circle, that's the symbol for composition. So this is f composed with g of x. This little circle means composition. Composition of two functions. Now what the heck does that mean? I'll show you. Here's what it means right here. You ready? It means f of g of x. Some students look at this and they see these things next to each other and they think multiplication. Please don't. It is not multiplication. With function notation, I think you should realize that you got input and output, sort of. Listen, who's the input for this g? The input for g is just the letter x, or the variable x. That's the input for g. Check this out. What's the input for f? G. The g function. See, this is what this says. This says, plug the entire excuse my language, plug the entire g function into the f function. That's what that says. And if you understand a little bit of math notation and function notation, like we've been working with this semester, then you understand that. That says plug g into f. Let's just try it. It's kind of strange, but you grab the entire g function, and stick it into f. Where do you stick it? Where you always stick stuff. Where do you always stick stuff? Into x. Right. So I get 4 times, I plug the entire g function in here. Minus 7. It's kind of strange, but it's the composition of two functions. And what it does is it creates a new function. This is a new dude. It ain't f, it ain't g, it's a new guy. It's the composition of f and g. I mean, I could clean it up. I could distribute the 4 and gather a couple like terms together. You guys okay with this? Distribute the 4, gather a couple like terms together, and here it is, the composition of f and g. It's a little more fun to do it with a number. Watch this. G composed with f of 1. G composed of f of 1. So now I'm not plugging in an x, I'm plugging in a 1. But what am I doing? Hang on, let me show you the other way to write it. I wrote it 2 ways over here. I wrote the composition with the little circle notation. But then what is that? It means this. And so let's here, let me try it with this 1. So in other words, this means g of f of 1. So forget the dang circle for just a second. If you saw it written like this, would you know what to do? I'm saying you should, but it might be kind of new. It's new to you here. What's also new to you is the circle notation of composition. But when you read this, I think you should understand it. Here's how you do this. You work your way from the inside out. I think what this says is, please plug a 1 into f, is what it says. Please plug a 1 into f. Let's just do that. When you do plug a 1 into f, I go over to the f function, I plug in a 1, what do I get? -3. Okay, hang on. I get negative 3. But that's this answer, you guys. That's negative 3. Now, what am I supposed to do with that negative 3? Plug it into G. Yes, ma'am. Now it's sitting there waiting to be the input to G. It's a little two-step process. You plug the 1 into F, you get your answer, and you plug it into G. That's what that says. It's kind of fun with a number. It's kind of a pain when I had to plug the entire function in there. It was a little different. I plugged the entire function in there, just distribute it. But with a number, you plug a 1 into F, get your answer, take your answer and plug it into G. I'll just finish this real quick. That means I got to plug a negative 3 into G. 2 times 9 minus a negative 3 plus 3. I think that's 18 plus 3 plus 3. I think that's 24. That's the answer. You guys okay? Any questions?
You did my job.
Oh, all right, good. Here's the more difficult one here. So I did F composed with G. Let me try G composed with F. Actually, I just did G composed with F. Hold on. I did G composed with F with a number. It's kind of fun with a number. You plug a number in, plug a number in. But it is a little two-step process. You plug the 1 into F, you get your answer, and plug it into G. It's a little two-step process. You plug your 1 into F, you get your answer, plug it into G. When it's just G of F of X, then there's no number to plug in, so it's kind of like the first step is not even done. I mean, here's what this means. This means G of F of X. And so we've already got X plugged into the function. Where's X plugged into F? Do we have X plugged? Yeah, here it is. Here's X plugged into F. But now what am I supposed to do with that F function? Plug it into G. And that's a little bit of a pain. Watch. That means I got to plug F into G. Hold on. I got to plug F into G. That means I got to grab this whole F function and do what? Plug it into G. Where do I plug it? Right there. And right there. And maybe do a bunch of simplifying, maybe.
So you gotta write it twice.
Well, I'm plugging it into X. So what am I? Okay, now hang on. What am I plugging in there? So I'm going to plug something in and it's going to get squared. What am I plugging in? The 4x minus 7, thank you. Right. And then minus x. But what am I plugging in for that x? 4x minus 7, thank you. And then plus a 3. So this way is a little tougher because now if I want to simplify it, what do I have to do? Some foiling. Foil first. Foil first before you distribute. Foil it first, distribute, collect like terms. I mean, it's some work, you know. Don't want to do that work?
Not really.
All right, I'll do it. I ain't scared. Hey, I've been foiling these things out, and I've been trying to tell you that it is 16x squared plus 49. What did I just do? I squared the first guy, I squared the last guy. Is that what I did? But there's a middle term, and the middle term is always the product of those two guys doubled. It always is. There's a middle term, and it's the product of those two guys doubled. What the hell? That's 28x doubled. Negative 56x. That's the middle term you get when you FOIL a binomial like that. Square a binomial. What's this? Negative 4x plus 7 plus 3. I distributed the negative sign. I got to distribute the 2. I'm going to move way up here, you guys. Sorry. 32x squared minus 112x. If I distribute the 2, plus 98 minus 4x plus 10. Wow. 32x squared minus 116x plus 108. I told you, that's kind of hard work. Oops, I lost something. 32x squared. That's the answer to this composition. I had to move way over there, sorry. Up there. I'm trying to teach you about the process of composition. The truth is, composing composing these guys isn't the most interesting thing. Let me show you where it does get a little interesting. It gets interesting when you compose, watch this. I'm going to get rid of these. Hopefully you understand these. Watch this guy. F of x is x divided by 7. And g of x is 7 times x. What is f composed with g? I know, what does that mean? F composed with g. What does that mean? Stick g into f. Stick g into f. That's how we read that. It's not weird. It's not backwards. It's not stick g into f. It means this. Here, I've said it 6 times. Here it comes again. It means f of g of x. It means stick g into f is what that circle means, that composition means. Check it out. If you stick g into f, this is kind of cool. That means you're taking the entire g function and sticking it in there for x. So what do you get? 7x over 7? What is that?
1.
Not really 1, well, but what is it? It's sort of 1. It's x. It's 1x. It's not 1, but it is 1x. Yeah, it's x. You know what's kind of funny? Is you stuck, read this back here. You stuck x into g, then you took that answer and stuck it into f, and what's the final answer? X. I mean, the original input was x, and after going through this process, you got the output is x. You're back to where you started. You know why you're back to where you started? These two functions are kind of cousins. They canceled each other out. One of these functions divided by 7. What did the other function do? Multiply by 7. When you compose them, they cancel each other out and you end up with x. Those are special functions when that happens. What did I call them? Cousins? That's just, no math book calls them cousins, but I call them cousins. Let's try another one. This is getting somewhere. We're getting somewhere now. Check this out. Here's one. F of x is the cube root of x. G of x is x cubed. I mean, you may notice that those guys kind of look like cousins, don't they? Yes. Whatever that means. But if you compose them, they do cancel each other out. They do. Not if you multiply them. I'm not saying multiply them. I'm not saying them. That's not the word I'm using. I'm not saying add them. I'm not saying subtract them. I'm saying compose them, which means plug one function into the other one. So if I did f of g of x on this one, I would, let me think now. I'm plugging g into f. Hold on. I'm plugging g into f. So I'm plugging this cubed function into a cube root. So now I have the cube root of something cubed. What is the cube root of something cubed? X. So when I plugged it in, it's sort of like they canceled each other out and you just get x. It works the other way too. I did f of g of x. What if I did g of f of x? In fact, what was that? Wait a minute. What's the difference? Hang on. What's the difference? Now I'm plugging f into g. Now I'm plugging f into g, which means I'm taking that cube root function, and what am I going to do with that cube root function? I'm going to plug it in here for x, and I'm going to cube it. So now I'm going to cube it. Well, cubing a cube root, cancels out, and you get x. So you can do composition for the hell of it, kind of how I started today, but the real purpose maybe to me of composition is to see how some functions have this special property where they sort of cancel each other out. And this leads me into chapter 5, you guys. Here I go. If, I want to say this, if f composed with g of x turns out to be x, and g composed with f of x also turns out to be x. I'm saying if you do the composition, like we just like these examples, if you do f of g of x, you get x, and the other way, g of f of x, you also get x, then those two guys are special. They have a special relationship. I call them cousins. The real word is this: f of x and g of x. I should say, if that happens, then this happens. F of x and g of x are inverse functions of each other. Inverses of each other. And that brings me here into into 5.1, inverse functions. So I'm going to keep talking. How you guys doing? All right. All right. Thank you for listening. Yeah, inverses of each other. Let's try these. Let's try this guy. F of x is x plus 4 divided by 3. And then here's g of x. G of x is 3x minus 4. I mean, these are two different functions, but I wonder if they're inverses of each other. I wonder if they got this special relationship where they cancel each other out. I wonder. In order to test it, to see if they are inverses of each other, I should sort of do this. I mean, this is, I kind of just learned that if these two guys are going to be inverses of each other, then this happens. F of g of x is x, and g of f of x is x. You know, these two examples I had up here were kind of easy to see. X divided by 7, and then the other one was 7 times x. Were they inverses of each other? Yes. They kind of undo each other. One does something, divides by 7, the other undoes it. It multiplies by 7. Then I had a cube root and a cube. Those undid each other. Whatever one function did, the other one undid it. Right? One function cubed it, and then the other function cube rooted it. Brought me right back to where I was. Well, when you start putting 3 or 4 or 5 damn steps in the problem, it gets a little trickier. Like this one. This is not 4 or 5 steps, it's 2 steps. But when you have these 2 steps, it gets a little trickier. These guys, let's see, what's this doing? This one's adding a 4 and then dividing by 3. I mean, I'm trying to say, what does this function do? This function adds 4 and then divides by 3. What does this function do? Multiplies by 3 and then subtracts 4. Hey, that does seem like the opposite. In fact, it seems like it's doing the opposite stuff, listen, in the opposite order. That's also true. See, hold on a second. I want to write down something. What does f does? What does f does? What does f do? I want to write down what f does. And I just said it, but I want to write it down. What does f do? And if you take an x, you have to imagine what you would do to this x. If you plugged a number in, what would you do? Tell me. Add 4, and then divide by 3. And you would do it in that order. It's important. The order, right. So you would add a 4, and then you would divide by 3. I'm just kind of writing in order what f does. Check this out. What does g does? What does g does? What does g do? Let's write down what g does. If you plugged in an x, you would multiply by 3 and then subtract 4. In that order, you would multiply by 3 and then subtract 4. Dude, I think that's it then. I think they're inverses based on this little. This is what f does, and it looks like g kind of undoes whatever f does. It does. Are you hearing me?
Yeah.
All right. But a few minutes ago, I had this little test. We could run through this test. Let's do this little test. I want to try f of g of x. Now, what does that mean? stick G into F. Okay. Grab this G function and stick it into F. Okay, here I go. Where am I sticking it? Right there. All right, I'm sticking this in there. It's going to be 3x minus 4. See, I'm sticking it in there, and then I still have the plus 4 and the divided by 3. Oh, it's so easy to see, can't you? I mean, once you plug it in there, you can see. The 4's cancel. You're left with 3x over 3. The 3's cancel. You're left with x. Yep. Awesome. Let's do it the other way, though, because, listen, this little rule said it's got to work both ways. So let's try it the other way. I want to try g of f of x. Okay, g of that. That means take f and stick it into g. All right, that's a little different. It's a little different. I'm going to grab the f, and I'm going to stick it into g. I'm going to stick it right in there. So here I go. I'm going to write 3 times. Now, what am I plugging in there? F. X plus 4 over 3. And then I'm going to subtract 4. Again, once you fill it in and do it, you can sort of see it. I mean, the math says maybe you should cancel these 3's. And then you have x plus 4 minus 4. So what is that? That's x. So we just proved it in a way. When I wrote these up here, I already knew what was going on. But what the conclusion here is that F and G are got this special relationship. Again, I could call them cousins, but they're inverse functions of each other. They undo each other. They're inverses of each other. I want to say these words. They undo each other. Hey, they don't do each other. Don't say that. That ain't nice. They undo each other.
Is that function on reciprocating?
You know, this kind of has this. No. That word inverse sometimes gets confused in mathematics with reciprocal. It's not really the same. The word inverse functions are undoing functions. Anyway, they're not reciprocals. There might be some special cases where it is a reciprocal. Kind of like these. Hang on, back to this one. This function multiplies by 7. This function divides by 7. You could refer to the 7 and the 1/7 as reciprocals, but it's bigger and broader than that. So to equate the word inverse with reciprocal gets you into trouble sometimes, right? When we find out that they're inverses of each other, listen, then we can name them this special name. See, now that I know that F and G, they are inverses of each other, then I could call G, oh boy. When we have a function F, we call his inverse this. F inverse of X. We use a little -1. That also might make you think of reciprocal. I'm sorry, it's not a reciprocal. It's a little -1 notation. Listen to this. It's written up there like it's an exponent, isn't it? But it ain't an exponent. It ain't an exponent. We need to talk all about exponents in Chapter 5. In Chapter 5, we're going to learn about exponential functions. We're going to talk about exponents. We're going to talk about negative exponents. But anyway, that ain't what this is. I'm sorry. This is just a little notation. It's not an exponent. It's a little notation that means what? What does it mean? This is a function f. This is a function called f inverse. It's his cousin. And it ain't 1 over. It's the undoing guy. It's not an exponent. It means f inverse of f. It means if you compose them, they would cancel each other out and give you x. These guys, this f and g are inverses. And so maybe I should rename g f inverse. Or I could rename f g inverse. Let's do a different problem. So now I want to teach you how to find an inverse. So what have I done so far? I've given you two functions and kind of said, prove that they're inverses. You know, try to see the composition relationship that proves they're inverses. Now I want you to find your own. So watch this. How to find f inverse. Okay, here we go. Here's a function. Okay, that's a function. It's not too hard. Now listen, I got a couple different methods for you here to find how to find an inverse. The first method is called, I made it up myself. It's called the Smith method. It's famous. No, it's not. It's only famous in this classroom. It's the Smith method. Here's what you do. You got to write down what f does. Let's write down what f does. What does f does? What does f does?
Multiplies by 5.
Okay, multiplies by 5 and adds 8. All right, that's what f does. Well, now what I'm trying to do is find f inverse. Watch this. I'm trying to find f inverse. This is my job, to find this inverse function. And so what I'm saying is I gotta go look at what f does, and I gotta undo what f does in reverse order, in opposite order, in reverse order. So here I go. Look, this is how I do it. I got a big space out here where I'm going to write some stuff. First, though, start with an x. Now, what are you going to do to that x? You're going to undo this stuff in opposite order. So what are you going to do to that x? You're going to subtract 8. Good job. You're going to subtract 8.
And divide by 5.
After you subtract 8, you're going to divide by 5. Awesome. You just found his inverse. I gave you this function, and you found his inverse, and you did what's called the Smith method.
So you just switch numbers around, basically.
Well, I don't know. You guys like to change. This is the process. I mean, yes, some stuff got switched. Multiplication got switched to division. Addition got switched to subtraction. The order got switched in which we did it. In this function, you multiply first, then you add. In this function, you subtract first, then you divide. I mean, a lot of stuff got switched. Definitely, a lot of stuff got switched. Watch this. Here's the book method. So this was the Smith method. How to find an inverse. You got two methods. You got the Smith method. Smith method is pretty cool. But then there's the book method. The truth is, well, I don't know if I should tell you. Well, the truth is the Smith method doesn't always work. Pretty great method, but not always. The book method always works. Check out the book method. The book method is this. Step 1, switch x and y. See, when you do the book method, you're just a robot. When you do the Smith method, you kind of know what's up. Your f does something, you're trying to undo that. The Smith method is kind of instinctual. The book method is just very robotic. You ready? Step 1, switch x and y. And it's kind of mean. It's kind of got an attitude. Step 1, switch x and y. Step 2, solve for y. That's the book method. Just shut up and do it. Sorry. Is that all that? Is all that crap on video? All right, here we go. Let's try it. Let's just try the book method for this problem right here. Okay, so what's going on? They say step 1, switch x and y. All right, so that, by the way, that's my y, right? Is that my y? That's my y? So call it x. This is my x, so call it y. Okay, so I just switched my x and y. Step 2, solve for y. And if you solve for y, you're going to do algebra, and you're going to do the algebra that the Smith method told you to do. You're going to subtract an 8, and you're going to divide by 5. I mean, it's cool. It works. Anyway, I mean, it works. It's awesome. The book method works. So does the Smith method sometimes. It's really the same thing. It's really the same thing. Kind of. Hey, by the way, when you get done here, this y is not the original f of x. Remember, you switched your x and y. So this y is f inverse of x. Okay? In other words, we should call this answer here, this final answer here, the inverse of x. You know how y is usually the function. Well, y is the function, but it's the inverse function of that original y. This works, you guys, and it works with more complicated functions. You really need this method. You might be looking at these easy ones and saying this is too easy. Watch this. You need it here. You need it here. Here we go. Let's do a better one. 4x minus 7 in parentheses cubed divided by 5 plus 12. All right, good luck. Find his inverse. This is good stuff now. Welcome to advanced college algebra. No, I'm just kidding. But you can't stay too basic too long. You got to step it up a notch. This is good. Hey, I want to find his inverse. Which you guys got, the Smith method or the book method? Which one do you want to do? Come on now. You're supposed to say Smith method.
Homework's gonna be on.
I mean, at least while I'm standing here, you should at least say Smith method. All right, so the book method or the Smith method, which one do you guys want to try?
Both.
Good.
I mean, can't you pretend to make me happy? Just pretend. They both work they both work good on this one. The Smith method makes you think about each step and what comes next, and then you got to do the opposite of that. It works good. The other one is more algebraic. You got to switch x and y and then solve for y. But it all amounts, in the end, it's the same. I'm going to try the Smith method. So if I'm going to do the Smith method, then I have to do this thing where I write down what f does. And that means I have to imagine plugging in a number, like imagine plugging something in for x, and what's the first thing you would do to x? First thing, when you plug something in, what would you do first? Yeah, I think the first, see, so you need to know your order of operations, kind of. If you plugged a number in there, I think the first thing you would do would be subtract 7. Well, you're in the parentheses. You got to do your parentheses. So I think you got to, if I plug a number in there, the first thing I would do is subtract 7. Okay, I'm going to write that down, subtract 7. After I subtract 7, what would you do? I would cube it before I do these other numbers. You're right. The exponent comes next. You're right. I would cube it. I'm going to just write the word cube it. Okay, after I cube it, what would I do? Multiply by 4, multiply by 4, then what? Divide by 5, yes sir, and then what? And then add 12. Good, you got it, you guys. That's what you should do. Wait a minute. That's what f does. Now what you want to do is you want to do the reverse of that. You want to undo f in reverse order. All right, here we go, here we go, here we go. Here's f inverse. Like I said, have some space to work and put an x out here, and then we're going to start doing stuff to that x. What are we going to do to that x? Oh, I'm going to subtract 12. I'm going to undo these things in reverse order. Okay, I'm going to subtract 12. By the way, whatever next step you do to the whole thing. So we subtracted 12, and what's the next step? Multiply by 5. Well, hold on. That means you do it to the whole thing. So put parentheses on it and multiply by 5. Then what? Divide by 4? Okay, well, divide the whole thing by 4. In other words, you're not just dividing the x by 4, you're dividing the whole thing by 4. Then what?
Cube root it.
Oh, cube root it. You got to do the opposite of cubing, so you got to cube root it. Okay, cube root it. That's a cube root. It's like a square root with a little index 3 up there. All right, we're doing good. What now? Add 7. And that's not in the cube root. That's kind of off to the side. This is going to go off the video here. Plus 7. Plus 7. We did it using the Smith method. You guys don't seem so happy about the Smith method. Yes?
We're going to be solving any of these, like multiplying them out and stuff?
I mean, no.
Okay.
Maybe no. The question was, given a certain function, can you find his cousin? Or his inverse function? And it's kind of hard. It's, well, you need a method. And the Smith method works, but the book method also works. The book method works. The book method, I mean, it's kind of fun to do both, but I don't really want to do it again. But, yes?
You know how you said the Smith method doesn't always work?
Right.
Will that apply to the stuff we do in class?
Well, so then you might run into a homework problem where the Smith method doesn't work, right? Right. Right. In your homework, there's some little tougher ones where I can't figure out how to get the Smith method to work. So then when the Smith method doesn't work, I call it I don't want to call it the Smith method anymore.
But we can use the Smith method on our test.
Well, you can.
Where does it break down, though? Where does the Smith break down? Like, not work?
What do you mean?
How would it work?
Well, all right, so you want to know why it doesn't work.
Yeah.
All right, it's on here. It doesn't work on this.
Is there a way to know before you do the whole?
Well, here, I'm going to tell you. It doesn't work on this. It doesn't work on this. The Smith method doesn't work on this. Because you're dividing by x. And so I can't really figure out how to say that. Watch. If I want to write down what f does, so what's the first thing f does to x? I divide. Do I divide by 3? No, that's not the right. No. I don't divide by 3. Do I multiply by 3? No. I divide x into 3. So what am I doing to x? I have a hard time saying what I'm doing to x. You with me? I can't really say divide by 3. I can't say multiply by. I can't say divide into 3. It kind of fails.
Okay, we go to the book method.
All right, let's do the book method then. The book method should work. How do I do the book method? Switch x and y. So now what you got to keep in mind, this is y. So it becomes x. And then this becomes y. And now what? Yeah, that's it. That's easy. Switch x and y, and then what?
Subtract 4.
Well, and then solve for y. Right. Solve for y. When you get y by itself, you'll have the answer. Now, solving for y might be a little tricky on this one, but you can do it. You can do it. You said subtract 4. I kind of like that idea. Let's subtract 4, and then I got this. But if I'm going to solve for y, I kind of need it out of the denominator. How do you get y out of that denominator? Multiply by it. Yeah, multiply by y. So you're right. Multiply this side by y, and multiply this side by y. Exactly.
And the y's cancel.
The y's cancel on this side, and he shows up over here. Now how do you solve for y? Now I don't want to distribute. If I want y, I can get him now.
Would you move the x minus 4 over?
I would move the x minus 4 over. It is multiplied by my y, so what should I do? Divide by it. Yes, I should divide by this quantity. So now y becomes 3 over x minus 4. Yep, that's it. And that's my inverse. You can do it. Switch x and y and solve for y. Do the algebra like we just did. But when he's down in the denominator, it makes the algebra a little tougher, maybe, if you felt that was tough. It's not too tough. But it also makes the Smith method fail. When you got an x in the denominator like that, I can't get the Smith method to work.
Thank you for that.
I want to show you something. I want to go back. I want to use these two examples. Okay, I'm going to keep talking about inverse functions. I'm going to talk fast here. You know, for this function, if I made a little chart of points, you know, for this function, I want to try a couple things. Plug in a -3. What do you get when you plug in a -3? I'm just talking about this function f here. It's pretty easy. Plug in a -3, you get -7. -15 plus 8, -7. Just x's and y's, right? Just x's and y's. Okay. Plug in a 0 for x, please. What do you get? You get 8. Plug in a 1 for x. What do you get? 13. Okay. Plug in a 2 for x, I guess. I don't know. 2 for x, you get 10 plus 8, 18. All right. All right. So then I can plot these points on a graph if I wanted to. These are just x and y points, you know. Check this out. If I made a little chart for this guy, watch for this guy. He's a separate function here. And I keep calling him, he's related to him. He's his cousin. They undo each other, but he's his own function. He's his own separate function is what he is. Check this out. When you plot points on this guy, watch this. All right, I don't know, but let's just try a -7. Plug in a -7, what do you get? -7 minus 8, -15 over 5, -3. Oh, I don't know here. I'm just going to try something. I'll try an 8. I'll plug in an 8. What happens when I plug in an 8? I get 0. I don't know, you know what I'm doing. I'm just going to plug in a 13. Plug in a 13, please. 13 minus 8. 5 divided by 5 is 1. You guys noticing anything?
So the y go back on the other side.
You not noticing anything? Hey, the x's and y's for the function are switched.
So on the
Which
graph-
goes back to, hold on, which goes back to the book method concept of switching x and y. If you want an inverse function, you switch x and y. There's a connection there. But this is different. If I plot a bunch of points for f and make a chart, I have a bunch of x's and y's. Guess what is always true for all inverse functions? If you plot points for the inverse function of f, all his x's and y's are switched. All his x's are now his y's. All his y's are now his x's. That's the way it is. That's the way it is, always. That's a concept about inverse functions. It's because they undo each other. Look. Plug a 0 into this function. What do you get? 8. Okay, now take an 8 and plug it into this function. It's going to undo everything that one did and bring me right back to 0. You plug a 0 into him, it sends you off to be an 8. Now plug an 8 into him, it brings you right back to be a 0. They undo each other. If I plugged in an 18, I would get 2, just to finish my chart.
I'm going to be graphing any of these.
Now I want to graph these guys. That is what I want to do. Because there's another connection here. So these are some concepts about inverse functions, you guys. You're getting some concepts about inverse functions. If you compose them, they cancel each other out and you get x. If you make a chart, the x's and y's are flip-flopped. If you graph those charts, if you graph these points, you'll see what that means. Watch. -3, -7. -3, -7. 0, 8. 0, 8. That's pretty steep. Huh. 1, 13. That's pretty steep. 2, 18. All right. Anyway, it's a line, you guys. Maybe you knew that. Oops. That's F. There's a picture of F. He was a line. He was just a line. Maybe you knew that. He was a line. Hang on, let's look at him. He was a line. He had a y-intercept of 8. He had a slope of 5. Remember that stuff? Okay. That's what he was. There's a picture of him. We plotted a bunch of points. Watch this. If we plot pictures of this other guy, watch this. I mean, if we plot the points of this other guy, -7, -3, -7, -3, 8, 0, 8, 0 is here. 13, 1, 13, 1. If I connect those dots, I get this picture. That's F inverse. All right, there's a big concept deep in that picture. Do you see some kind of symmetry there?
They're opposites, but they're still.
I mean, all those ordered pairs are switched. I mean, when somebody plotted 0, 8, the other guy got 8, 0, you know, and that happened for all these points. -3, -7, -7, -3. And the result of that is this picture. And this is always true. Inverse functions have this symmetry. What's kind of hard to see is where is that line of symmetry? The line of symmetry is here. It's this diagonal line right here. This acts like the mirror. This is the mirror, and these two functions are reflections around that mirror. Does that look like right now? Does it look right? When this guy comes in and hits the mirror, the other guy comes in and hits the mirror. When he goes to the other side of the mirror, the other guy goes to the other side of the mirror. This diagonal line right here is just a line called y equals x. You might remember that from, it's just a line that goes through 0, 0 and has a slope of 1. It goes up 1 over 1, up 1 over 1, up 1 over 1. That's a very basic diagonal line called y equals x. That acts as the mirror. And all inverse functions are mirror images of each other around that mirror, always. And that's a result of this stuff. That's the visual result of this idea. The damn x's and y's are switched in the chart. The result of that switching all those x's and y's results in this visual, always. Yes?
So,
Yes.
absolutely any inverse function will always have that mirror in that exact spot.
Yes, that's the mirror. The mirror doesn't move. That's the mirror. Yes. Yes. Yes.
Will they also, like, the lines have similar slopes and stuff?
Well, if they don't have similar slopes. This guy had a slope of 5. This guy had a slope of 1/5, I think. I mean, they're different lines. There's really nothing the same about these functions, but they have this relationship with each other, that they're inverses of each other, and they have this. Listen, let me do, watch this. So can you find this guy's inverse? Watch this. Oh my God. All right. So there's a function called f of x. If you have, did you take art before you came to this class?
No.
Oh, you needed an art class. I forgot to tell you. No, I'm just kidding. But I wonder if I can do this. I wonder if I can draw his inverse. I can't calculate his inverse because nobody gave me an equation. But I got this concept now that here's the mirror. Where's the mirror? The mirror is here. The mirror is this perfect diagonal line called y equals x. It's right here, cutting right through here perfectly. That's the mirror. So now can I draw the inverse function? Jesus. You know, this guy's flipping out that way, so I think my inverse function might flip out this way. Is that okay with you? That's a mirror image. And then when he comes in and hits the mirror, I think my inverse function ought to hit the mirror. Then he's on the other side of the mirror, so my inverse function should go around that side of the mirror. Hey, he hits the x-axis at, like, I don't know, maybe -1. Well, then this guy probably hits the y-axis at -1. then what does he do? He makes this big bend. Then, oh, he hits the y-axis at maybe, let's call that 6. So this guy ought to hit the x-axis at 6. He's got to have this big bend. I'm getting a little, I'm not doing too great. Then what? Then he's headed toward the mirror. So this guy ought to head toward the mirror and come out the other side. That ain't bad. That's a picture of F inverse. It's kind of tricky to draw a mirror image. I've had practice. And you probably don't really have homework questions like that. I like that question, but you can't really draw on my math lab homework. But you could on one of my tests. Listen, I'm about to try to finish this topic 5.1, and then before I leave today, I kind of want to get into 5.2 a little bit, but I got a little time. But here we are at the end of 5.1. It starts to get a little weird and scary, and that's, I'm sort of heading into pre-calculus. But let me just try to say a couple things. This gets kind of tough, though. Look at this. Never mind. I didn't really do a good picture. Sorry. Here, let's do another one real quick. A real fast one. You ready? Here's one. Here's one. So here's a function. Can we find his mirror image? Well, where's the mirror? Here, let me draw the mirror. The mirror's here. Right? That's the mirror. All right, now I want to try to draw his mirror image, his inverse. Watch this. Watch this. I want to draw his inverse. Oh, boy. It's tricky, you guys. I'm just going to do it for you. Oops. It's that. Are you okay? Are you okay with that? Do you agree? Does it look like a mirror image after I'm done? Does it look like it? It's kind of tricky just to do on your own. But after I'm finished, does it look right? I think it is. That's the mirror image. Isn't that the mirror image?
I would say it was.
And then that gets flipped over, and then this gets flipped over. Look at each. If you want to look at each little part, this little part's the mirror. They're all there. It's the mirror image. This is the mirror. That's what's weird. You got this diagonal mirror. Here's the thing. Listen to this. Is the original function f, is he a function?
Yes.
Yeah. How do you know f is a function?
Because only
Yeah.
the x.
Every x has only one y. It passes the vertical line test. It passes the vertical line test. So it's a function. The original guy is a function. But when you flip him over and look at his inverse, look at his poor inverse. Is his inverse a function?
No.
No, because it fails the vertical line test. And the reason the inverse is not a function, see, this is the part that gets a little tricky here. He's not a function. I mean, I can explain it. You can understand it. Listen, he's not a function because he fails the vertical line test. Well, that's because his original function, before you flipped him over, well, wait a minute. The original guy was a function, wasn't it? Yeah, but look, you know what? The original guy fails, and you never knew this. He's a function, but he's not a one-to-one function. He's a function, but he's not a one-to-one function because he doesn't pass the horizontal line test, does he? And if you fail the horizontal line test, you might still be a function, but when you flip your inverse over, your inverse won't be a function. If you fail the horizontal line test, your inverse is going to fail the vertical line test, guaranteed. That's So what the hell did I just say? This might be in some of your 5-1 homework just a little bit. And I just want to write this down for you. What did I just say? If the original function passes the horizontal line test, which you never heard of before, because it never was too important before. But you know what it is. The horizontal line test means you draw a horizontal line and only cross it once. So if it passes the horizontal line test, that means it's called, the function is called 1-to-1. 1-to-1. And that means his inverse function is going to pass the vertical line test. You guys okay with that? Is this logic okay? You following this logic? The original function passes the horizontal line test. That means he's called 1-to-1. What that means is his inverse is going to pass the vertical line test. Therefore, his inverse is a function. And you could go through, you could write 4 more sentences that say the opposite of this. If you don't pass the horizontal line test, you're not 1-to-1. Therefore, your inverse won't pass the vertical line test. Therefore, your inverse is not a function. I'm not sure how much I'm going to ask you about that, but your book your homework might kind of say, might kind of worry about that. Is it 1-to-1? It's not hard. It's very visual. Is it 1-to-1? Does it pass the horizontal line test or not? This one is no. This one is not 1-to-1.
What does 1-to-1 mean?
Passes the horizontal line test. See, to be a function, we always had, every x had to have only one y. But we never cared whether one y had too many x's or not. To be 1-to-1, one y has to be with one x, and one x has to be with one y. It has to go both ways now, right? Hey, we've done pretty good today, you guys, but I'm going to keep talking. Because to tell you the truth, this is kind of this 2-3 and 5-1. It's all kind of preliminary work. I mean, there's some test questions involving some of this when we get around to a test. But the big theme of Chapter 5 is, we're not even there yet, and I want to get there. You ready? The big theme of Chapter 5 is to study these 2 new functions, 2 more functions before this course is over. We've studied lines and quadratics and polynomials and rational guys with asymptotes. Anyway, there's 2 more coming here. They are exponential functions and the inverse of exponential functions, logarithms. So 2 more cool functions, and they're inverses of each other. That's why we stopped and discussed inverses for a little while. Okay? But that's the end of this chapter. That's the end of this course. 2 more new kind of functions. In 5-2, we can talk about exponential functions. And then in 5-3, we'll talk about the other one, logarithm functions. And then we'll spend a little bit of the chapter trying to see how they work together. So I'll probably work hard Thursday too with some good, I'll probably have some good lectures Thursday in 5-3 and so forth. But watch this, here's an exponential function. You ready? Check this out. An exponential function. Watch this. Let's say that the college didn't pay me. They didn't pay me to teach this class. And they made a deal where you guys got to pay me to teach this class. And so the deal was, you got to go back. We got to go back to day 1. And you got to pay me a penny. We'll start with her. She owes me a penny. And then the next day, somebody else has to pay 2 cents. And then the next day, somebody has to pay 4 cents. You following me?
No.
Okay, now you might want to get your calculators, but I just want to do this real quick. So we go back to the first day of class. She owes me a penny. You owe me 2 pennies. You owe me 4 cents. That's all. You got to bring it. Don't no check. I don't take a check. You're going to give me 8 cents. the next day, she's going to give me 16 cents, 32 cents, 64 cents, 64 cents. Now, by the way, what am I doing? What's the word here? I didn't say the word double. I'm doubling. Every day, I'm doubling my pay. You have to pay me double of the previous day. So now he owes me 64 cents, so you owe me 128 cents, which we could call $1.28, right? $1.28.
156.
You might need a calculator. $2.56.
$2.56.
$2.56. And we're getting better now. I might not even want those pennies. What?
$5.12.
$5.12 she owes me. $10.24. $10.24. $20 bill. That's a $20 bill, dude. And 48 cents. 20.48. Thank you. Wait, hang on. It was 20.48. Double it. 40.96. Is that right?
Yes.
Yeah.
40.96. You owe me 40.96.
$81.92.
$81.92. $81.92. I'm gonna remember that. $163.84. $327.68. This is getting good. 655. $655.36. Is that right? All right. 655. Okay, let's just call it 655. He owes me $655. You owe me $13.10. Well, I'll give you the cents. Don't worry about the cents. $1,300. $1,310.
$2,620.
$2,620.
Nah, 5,000.
240. 5,240. $5,000. And then another guy owes me $10,000. Something. 10,400 and something. And finally, $21,000. $21,000. I guess what? That's not true. They really did pay me. I'd rather have that pay though. And I really wish more people came to class today. Because the next guy would owe me $40,000. The next one, $80,000.
That's on the day, right?
Well, you're doubling my pay every day. And the point is, it starts kind of slow, but increases very rapidly, very quickly. The word for that is exponential growth. And that was a classic example of an exponential function. Now hang on, we ain't leaving yet. Let's go back to what we just did. You know, instead of day one though, when she paid me a penny, I want to call that day zero. So on day zero, she paid me a penny. And then the next day, and the next day, and the next day, and the next day. So what happened the next day? I got 2 pennies, 4 pennies, 8 pennies, 16, 32 pennies, 64 pennies, $1.28. You know what I want? This is the chart of what y'all just did. We just did this. What's the equation for this function? What's the equation for this?
X equals y squared.
2x.
Plus 1 times 2.
And it's a little tricky. It's kind of a new idea. Listen, I hear you guys talking. I appreciate your input. You are doubling my pay, but 2 times x is not the answer.
Is it e to the x?
Well, and it's not e, but it's not x squared. It's kind of, these are all good guesses, but they're not the answer, especially if you look at these numbers.
Something double.
Oh, 10.
Well, it's an exponential function. It's a new animal. You haven't studied it yet, but maybe you have somewhere in high school. But listen, here's what it is. I'll tell you. It's 2 raised to the x. And what's new and wild about this is the variable is up in the exponent. And when that happens, that's a whole category of things called exponential functions. When the variable is up in the exponent, that's a whole new category of things called exponential functions. And if you check this out, please plug in a 0 for x. What happens when you plug in a 0? Well, you might need to recall some exponent rules. 2 to the 0 is 1. Anything to the 0 power is a 1. This is just 2 to the first. This is just 2 squared. This is 2 cubed. This is 2 to the fourth. This is 2 to the fifth. You ready? Right? Hey, I wonder what would have happened if I would have had 30 students in class. What would student number 30 have to pay me? 2 to the 30th. Can you guys please do that? You got a calculator? You're going to need a calculator in this chapter, and you're going to need to learn how to use your exponent button.
10, 7, 3, 7, 4, 1, 8, 2, 4. There you go.
This is what student number 30 has to pay me?
Yeah.
Is it?
Yes.
Well, some of you have a 2, and then you have this little button, raises it to the 30th power. Some of you might have what's called a y to the x button, where you type in 2 as your base. The 2 is called the base. This is called the exponent. But you hit 2, you hit this button, and then you hit 30. You should get a calculator and find your exponent button and learn how to use it. It's usually this one. But now, hang on, am I trusting him? Did anybody else do this?
I got that.
This is the number you got. And where's the decimal? Right here?
Yeah.
Okay, now hold on. Now this is pennies. So if I want to make it dollars, like what did I do with this? This was 128 pennies. So to make it dollars, I moved the decimal over here, right?
Yeah.
So this is pennies. So if I move a decimal right here, now it's dollars. And what the hell is it? Holy baloney. 10 million. $10 million, $737,418.24.
You better get an A.
And pennies.
No, it's dollars. Now it's dollars. It was pennies. Here, it was this many pennies, but I moved the decimal over, so now it's $10 million.
Yes, but your pay requirement was pennies.
Oh, in pennies.
Yeah.
Oh, I got you.
So big.
Let me show you. I got 30 seconds. Here's what this graph looks like. This y equals 2 to the x. I plotted a 0 and I got a 1. I plotted a 1 and I got a 2. I plotted a 2 and I got a 4. It keeps doubling. I plot a 3, I get an 8. Listen, you guys, it is steep. I mean, these things are steep over here. When you plot a -1, then you got to know what 2 to the -1 is. Do you guys know what that is? See, now I got to remind you of some exponent rules. A negative exponent is not a negative answer. It means move him into the denominator. It means move him down and it's 1 over 2 to the first, or 1/2. Watch. What's 2 to the -2? 1 over 2 squared, or 1/4. What's 2 to the -3? It is not -8. It is 1/8. Negative exponents make things small. Anyway, so when you move here in the negative direction, this gets very small and approaches this asymptote. And this is a classic picture of exponential growth. This is, well, I want to study these graphs a little more. I got to quit now. Before you leave, let me hand you your tests. And if you want an updated look at your number, I got an updated look at your number. But first I'll hand you your test. Some of you are fading away. I mean, a lot of those people that are fading are maybe not even here. But it's, you know, it's the fourth quarter, and it's past the fourth. It's 5 minutes left in the game. We got to crunch. It's time to kick in. Chad ain't here. Brianna. You're welcome. Taylor. Cheryl. These are 80-point tests. You can divide and figure out what your percent is. Just
Yeah.
but I think you kind of need to work harder, some of you. Brandon's not here. Lynette. Brandon is not here. Coming to class and listening helps. I appreciate you being here, but then you got to work. I guess you got to do some homework. I think less and less people are doing that homework. But it might help to help you learn. Andrew. Jacob. Mel. Autumn. Mel. Maria. Ryan. Pooja. Lisa Marie. Ryan. Leah. Logan. Leah. Logan. Heather. David. Vincent. Kiana.